In this video we'll look at the graphs of parametric equations and also how to convert a parametric equation back into Cartesian form. So we have seen before that if we have motion in a straight line with a fixed point, in this case of 2, 4, and a direction vector of 3, 1, then we can express this equation for the line in terms of the x and y values, where x is equal to 2 plus 3 lots of some parameter t, and y is equal to 4 plus 1 lot of t. So there's our parametric equation, and it can be written in vector form as we have here. Now if we were to graph this, we have t is a member of the real numbers. If we let t equal 0, we'll get a starting point at 2, 4. If t equals 1, etc., we'll end up with a series of points. So here it's t equals 0, t equals 1, t equals 2, etc., and we get a straight line graph. Notice that the x component and the y component are both linear, therefore x will change at a constant rate, likewise y, and we end up with a straight line graph. Let's look at a set of equations. So here x once again is linear, but y now is not linear, so we'll see what difference we get in terms of the graph. So if we were to plot the motion, and we have once again t is 0, 1, 2, 3. If I let t equal 0 in here, I'll end up with 0 take 2, which is going to be negative 1. If I let 0 replace t here, I get 12 on 1, which is 12. And if we continue to substitute, if x of 1, we let t equal 1, we'll get 1 take 2, which is negative 1, and we'll get 12 on 2, which is 6. So we can do that in turn for each of our t values, and we get a series of points. If we were to plot those points, we'd end up with a curve such as that. Notice the entire function is no longer linear, although if you look at the x values, then going from my position here to my next x value, which is here, that's half a unit or half a square across, the next value is also half a square across, and each of the x values, if we move left to right, seems to be changing at a constant rate. Whereas the y values, we've got a big dip here, smaller there, and smaller each time we change our value of t. Now there are a number of bits of software that we can use to draw the graph. So here I'm using a parametric plotter. I've got t take 2 for my x component and 12 on t plus 1 here. And if we plot that, we end up with the sketch that I've got pasted back here. Your graphing calculator would do the same thing. So if we go to graph mode, and we need to change the type of graph into parametric. So if we go for type here, usually we do y equals, but now we want parametric, so F3. And I've entered in the t take 2, 12 on t plus 1, and if we were to draw that, we end up with the same curve we have here. We don't actually see the individual points, but if I go to trace, then I can actually jump between t values, but at this point I'm starting at t equals 0. If I push across, then I'm going up by 0.01 each time. So I can change that. If I go back to 0, if I go to my view window, and if I push upwards, the pitch here is 0.01. So if I change that to 1, and then if I were to draw my graph, you can see the graph is no longer a smooth curve. It's got these straight lines between successive t values. But if I go trace, so my first point is at negative 2, 12, which we have here. If I push across, now t equals 1, I'm at negative 1, 6, which is this point down here. And each time I push across, my t value is going up by 1 unit rather than 0.01 units. So changing the pitch will help you do that. So now let's look at changing the parametric equation back into Cartesian form. So if I have x equals 1 take t, y equals 2t plus 3, I'm going to rearrange one of these to make t the subject and substitute that into the other equation. So in this case, if I were to look at the first equation, that one can simply be rearranged to give me t would equal 1 take x. And therefore, if I substitute that into my y equation, I'll get y equals 2 lots of t, which is now 2 lots of 1 take x with a plus 3. And if we expand and collect that bracket there, I'll end up with a minus 2x and a plus 2, plus 3, so plus 5. Right, part B, once again, the x equation would be simpler to rearrange to make t the subject. So t would equal, I'd get x take 1 divided by 2. And therefore, if I substitute that into y, I end up with this expression here. I've got two fractions, common denominator there, I can see would be 4. So I'd multiply the second fraction by 2 for both the numerator and denominator. And if we expand and collect, we end up with that quadratic equation there. Next example, we're looking at the point of intersection of a parametric equation. So here is my parametric form here, meeting a circle, which is written in Cartesian form. So intersections would imply simultaneous equations where we substitute one equation into the other. So we'll substitute the parametric into the Cartesian equation. And we end up with one equation with one unknown, which we can then solve by expanding, collecting like terms. So we get two t values, t equals 3 and negative 1. So to work out the points of intersection, I would need to substitute each value in turn into my parametric equation to work out my point. So my intersection occurs at the point 3, negative 1, and also the point negative 1, 3.